All right, here's another polar, probably example, place where you use polar because, yeah, again, we just have D is the disk centered at origin radius 5. So yeah, that's pretty much a given. But that would be a pretty good one for polar. Otherwise, yeah, you have to go from this negative square root to that square root. So polar here would be theta would just go from 0 to 2 pi, and r would go from 0 to 5. So that would sweep out that entire region. Oh, I had radius 3 on my paper, but I put radius 5 over there. Okay. All right. So here's what we get here. So if I use polar, remember, to convert this over to polar, a couple of things. Yeah, that, again, you can do it by substituting x cosine r, y sine r. Say it right. You can do that by substituting r cosine theta for x and r sine theta for y. However, what we noted was x squared plus y squared, that's just directly converted to r squared. So this is e to the r squared. And then the only little kicker about dA is not dr d theta, dA is r dr d theta. Tongue twister there. Yeah. So that just had to put in that extra r, which is very nice in this particular case because with that extra r, and then our limits, yeah, you're doing the r's first, so 0 to 5, and then 0 to 2 pi. Yeah, so this particular problem works out very nicely because doing the r's first, that's going to work out real nicely for u substitution in it. U is the r squared, and then du would be 2r dr. So du over 2r, yeah, that's going to cancel out that r, so it works out very nicely here. E to the u, and then we got r, and then dr is du over 2r. Yeah, so you just got 1/2 e to the u for a u substitution, so and so that's e to the u antiderivative, e to the u. But our limits are in r, so go back to r, that'd be e to the r squared. 0 to 5. So you got 0, 2 pi, so that's 1/2 of e to the 25 minus 1/2 e to the 0, well that's 1, so just minus a half. So you just have to now do the integration with respect to theta. Well, there's not a theta. This is just a number, this is just a number. So all that's just a number. So the antiderivative is just that number times theta, right? And theta is going to run from 0 to 2 pi. Well, 0's not going to give us anything there. Right? So it's just that times 2 pi. I forgot my half, didn't I? Sorry about that. Oh no. Oh, I wrote it as 1/25. Yeah, never mind, okay. I'm trying to check you guys. Stop me, all right. It's 1/2 times that. Not 1/25, I don't worry. 1/25. All right, so it's 1/2 e to the 25 minus a half times theta. So that's 1/2 e to the, well, if you multiply the 2 pi in there, what do you get? Pi times e to the 25th minus pi. So how are we going to write that? Something like that. Is that okay? All right. show you one more here. This particular type of problem. Let's say I have this double integral. It's already kind of specified out. So we kind of have to work our way back, if you will. All right, so I've got the double integral 0, 1, and then 0 to the square root of 1 minus y squared. And it's cosine x squared plus y squared, dx, dy. So the deal on that is, that's a mess. I don't think you could do it as it is right there, because integrate with respect to x first, and even switching, we did some where we switched the x's and the y's, the order of integration. That's not going to help because it's still probably going to leave you that. Anyway, probably not doable as Cartesian. So let's evaluate this thing by moving it to polar. It doesn't tell us what this particular region is we're integrating over, but so here's what we're going to evaluate by changing to polar, by converting to polar. Okay, so yeah, it's fairly obvious there, x squared plus y squared, that's going to be cosine of r squared. But this is x's and y's, and so let's think about what we've got here. As far as these limits are concerned, all right, so what are these right here? Well, since I'm doing the x's first, those are x's, right? I'm going from x equals 0 to x equals the square root of 1 minus y squared. And then this is telling me the y's go from, so put it in the inequality form. That's what that's telling me. I'm going from between that. And then these are the y's, so the y's are going from 0 to 1. Yes? So, it might be helpful to draw a little diagram of that. Because that's my D, if you will, what D looks like. And then I can maybe change that over to polar a little easier than. Okay. Well, y equals 0 to 1, that's easy. But what about, I guess the hard one is this one. X equals 0 is the y-axis. What is that right there? Well, again, it might be helpful if we think, I square both sides, move that y squared over, talking a semicircle. But in this form, I mean, that's a full circle. This is just half of the circle. Which half? It's when x equals positive square root of 1 minus y squared. Isn't that this half? If we have y equals square root of 1 minus x squared, that's the top half of a circle. So this is the right half of the circle, because it's x equals square root. With it. See the difference there? Okay. And so the y value goes from 0 to 1. So that's telling me I go from y equals 0 up to y equals 1. Is this sector right there? So in polar, what would it be? Pretty easy, isn't it? In polar, I just have theta goes from 0 to pi over 2. And the r is easy too, because you're just going from 0 to the circle 0 to 1. So we haven't come across anything too bad yet. Maybe that'll come later. All right, so we've got the limits now of the POA. Now we just need to get the rest of this converted. So let me write it one more time down here. So I know my limits. You do the R first, so it'll be 0 to 1 for R, 0 to pi over 2 for the theta. What am I going to do with this? So again, there's our x squared plus y squared, and that's just a direct conversion to r squared, isn't it? That's cosine r squared. Now, dx dy, that's kind of dA written out. So this is dA, and remember what dA in polar is? It's r dr. So again, works out very, very nicely. A little u substitution in it. Because this r here, yeah, we'll let the u be the r squared, and then that's going to help us out there. So it'll be 2r d theta, 2r dr, d over 2r, so 0 pi over 2, 0 to 1 for r, but it's cosine u times r, and then dr is d over 2r. So now we have 1/2 cosine u, which the antiderivative of that is cosine, the antiderivative is sine, positive sine, u. But these limits are in r, so u is r squared, go back to that. 0 to 1. And then we'll take care of the thetas next. Actually, could have split these up too, but so what do we got? 1/2 sine of 1 minus 1/2 sine of 0. Well, sine of 0 is 0. It's just 1/2 sine of 1 radian. That's not a nice value. So we'll just leave it at sine of 1. But yeah, now we need to, but the good news is that's just a number. So now we integrate with respect to theta, number, the antiderivative is just that number times theta, so it'd be 1/2 sine of 1 times theta, where theta is 0 to pi over 2. So plug in the pi over 2, like 1/2 sine of 1 times pi over 2, and then minus 0, well, that's good. So we just have pi over 4 times sine of 1. Said that sine of 1 is not a nice, quote unquote, nice number, so pi over 4 sine of 1. Good with that?